Yes. Hello. Hello. Yes. Is that okay? Closer. Hello. Hello. Hi. Hi. Okay. Hello. Walking around. Or... Hi. How are you? Yes. Is that and there any question or I talking to? Is that too fast? I think it's too round, right? Hello. Yes. I think it's about okay. I mean, this is my first time in India. Apologize if I speaking too fast. And also first time to deliver this kind of course as well. Back in Queen Mary University of London, I'm teaching on the material processing and manufacturing. But that is the all material. It's not just metal. It's not just additive, but it's for everything. Composite process, autoclaving or standard metal or ceramic, sintering, or yeah. But this is the first time. Normally, yes, yeah. And then another module I'm leading is actually material for aerospace application. Again, it's more materials module. It's not only mechanistic. It's actually metallurgy or material science of the material itself. So it will focus on microstructure, phase transition, something like that. Again, may I ask you, you have any background in that, or is you basically mechanical engineer? Yes. Mechanical engineer. Right. Okay. So I think it's 2:05. So shall I? Oh, another 2 minutes. Yes, sure. So this afternoon will be more about modeling. Now, how can we model it after we know a little bit about the general aspect? I believe the first part may be useful if you are a scholar, academic, or industrialist. This may good for grant application at the first bit. Yeah, I always want to remind myself all the time and keep update information. Like now, information for 2020 is basically not useful anymore. You need to talk about 2030, Mission 2050 for some country. Yeah. Yes, sure. Yes. Yes. The answer is yes. I think that's a lot of company trying to do, right? Yeah. Try to, yeah, and even these the new. I mean, the manufacturer will sell you with infrared diode IR infrared imaging equipment. But again, that's probably enough to basically get to print some high quality part. But again, that's what I said to you from industrial perspective. You need to do a lot of condition for that particular material, particular component, and then finally you probably licensing it or whatsoever. So it's still R&D needs to be done. Otherwise, you have quite experienced people to operate the machine, first of all, understand the part, and then I don't believe if you do it without any modeling, it's almost impossible. But model means different for different people. I mean, that's a good question because it's open to the lecture. Probably now it's 2:08. Shall we? Or we wait another 2 minutes? Right. But do we have a group photo at 3:30? Yes, yes. Yes, sure. So after this lecture, right? Right, 3:35, yes. Let's see. So we can move some of this slide to the other day. But yeah. Yes, please. Yeah, it has been done already. Yeah. Right. Yeah. Investment casting. This is my PhD project. Same-sex for. Yeah. Yeah. Yes. Yes, yeah. Yes. Yes. Mm. Yeah. Yes. Of course, the reason we use the investment casting because we want to remove the grain boundary, which is actually decreased about 3 times of the creep life of the materials, right? But you're talking about if you use additive. At the moment, with the powder-based fusion, I think it's probably difficult to control the thermal gradients. The way we introduce in investment casting, actually, we introduce a grain selector. So we control the kind of planar thermal gradients across the, the geometry we are using. And then you grow only 1 grains, right? Again, if you follow some paper from Professor Kohner from Germany, from Erlangen University in Germany, she using electron beam melting to fabricate about 5 millimeter thick single crystal. Already happened. The thing is they use scanning pattern. So to mimic the way of the spiral. So they scan like this. And then the thermal gradient actually quite planar kind of thermal gradient. And you can grow single crystal. But use electron beam melting is different process. So the thing they can do this or innovate this because they understand what's happening during the LPBF and electron beam. There are some differences which they can leverage. But if you can understand the thermal, we call thermal signature of the process, you may be able to design somehow the gradient that, similar to casting situation. And then hopefully you can grow only 1 grain. That is the dream, but it still is too expensive compared with casting because electron beam is expensive. And in order to do the, I just say mass production, is even harder. Yeah, because investment casting is still expensive. Don't get me wrong, it's very expensive because it's cast 1 by 1, right? Almost by hand. Yeah, from the wax loss process until machining to get the bread. Yeah. But anyway, it's still property of single crystal is a lot better than polycrystal nickel-based superalloy. Still, say again? Yeah, in the hot section. We cannot replace that at the moment. Otherwise, you have better material composition which can pitch to big aerospace company. Okay, I have this, for example, high entropy alloy which outweighs the performance of CMSX SAW, which I don't think no one yet trying to, because if you're good in strength, but you will not good in oxidation. and this cannot compromise or creep resistance. So that's why still CMX4 still better choice for them. Anyway, we can talk more on that. I think it's probably time to start the modeling section. And as I said, just to remind you again that the modeling section we're talking about is based on the powder-based fusion that I'm going to talk today. And then try to map this processing map of the metal in the wider picture. You will see that there's so many, even we call about welding or fusion, I would say fusion processes. You will see that there's number of methods that you can use. I mean, from the gas welding, resistant welding, arc welding, solid state welding, including, I mean, that I showed you before, friction welding, thermochemical welding, also another thing, which may be interesting for the recent sustainable energy kind of topic at the moment, quite hot. If you can use energy, hydrogen. But this is another matter of the corrosion or embrittlement in nickel, in titanium, basically nickel and then steel, which is a big problem. Again, that is another matter for the metallurgy. But for today, it's about radiant energy welding, or we call beam melting-based process. So we're talking about either fusion welding or electron beam or laser welding. And this LPBF is classified to be in this one for the manufacturing process. Anyway, in order to do all of that, I borrow one slide from University of Oxford about the process modeling that we can simulate. If you remember, in the morning we have the ring rolling here, that we want to understand the thermal distribution and subsequent phase, which is form of microstructure. You can simulate that in the ring rolling. You also can simulate the linear friction welding, rotary friction welding that I showed you earlier today. I mean, kind of friction welding. And this simulation is based on different strain rate. In this case, strain rate and also micro to macro scale simulation. If you want to simulate the chip of the machining here, this is quite high strain rate and also low, I mean, in the micro scale because it's quite small part, as well as this one. But in the bigger or manufacturing scale, like spin forming, or this is another forming, ring rolling, this require another physics, which is actually used. I mean, in short, this is solid mechanics and plasticity, blah, blah, blah. And if you want to look at more about plastic forming here, superplastic forming for the fan blade, titanium 6-4 alloy here, is actually you need to take care of probably some time phase transformation or some kind of phase change, solid-solid transformation here. Or also when you twist this one, you may want to know about this is hot creep forming. And then there's some other specific process which actually is subject to very high value added manufacturing. All of these are the case for aerospace application, which actually driven by Rolls-Royce UTC or Rolls-Royce University Technology Center at University of Oxford in solid mechanics. So that is the thing that I want to open. This is a process simulation that ultimately we want, hopefully someone or more people, more community that working on, or we have the community called computational mechanics society, I mean World Computational Mechanics Society, that will talk more about all this simulation. But for today, we talk more about the additive manufacturing. So again, I just want to emphasize again what you just mentioned about hot section of the turbine blade. Now there is a paper talking about how to print it already. I mean, back in 2016 in the Nature Materials, it's a commentary. But I mean, the summarize of this is actually successful adoption of the additive manufacturing or digital technology here to aerospace or more niche application like biomedical. It depends on the fundamental understanding of the material processing to develop some kind of data-driven, because people talking about data-driven or optimize the design of the component without actually understand the process, how you get to get the microstructure or those things. So this is actually key for the future. I mean, more like physical-based machine learning or a kind of reduced order model for some particular fancy component whatsoever. So the material interaction and also processing characteristic need to be captured somewhere somehow, because you want to predict defect sometime, most of the time microstructure and hence property. So this is about this talk today. So just rerun a little bit again. So we just want to print this kind of engine. If you remember this one, I will not take too much time here, but later want to emphasize here that, I mean, if you remember this video, I just want to emphasize here that, there's a lot going on in one just laser interact with the material here. So you may need to understand physics or multi-physics phenomenon in the process. You may want to understand, as I mentioned earlier, about chemistry, what is happening during this interaction. And you may need to use some sensoring or data science here to correct some data on real time. As you may know, some company already have a sensorization of the process to collect the data in that one layer. It's probably cost you about 16 gigabytes of data each layer. So it's just produce a lot of data for getting the temperature field or basically red spot for defect, for example. And that's dealing with engineering AI for sure. It's just one interaction here, material design. So this gives rise to the final product as well. Process design, as I said to you. Powder metallurgy, how you make your powder, also influence. The shape of powder influence the printability of your part at the end, like spherical or elongated powder are all contribute to the final property. Physical metallurgy, definitely what happens if it's subject to something we call intrinsic heat treatment. When you print something larger and below you intrinsically heat treated your below layer, and that's caused different transformation of the materials sometime as well. And solid mechanics for sure, which will stress that all these contribute to modeling of additive manufacturing. So now I want to define a little bit what is the process simulation of additive manufacturing, especially melting-based process. So when people talking about modeling, I think that means different from different people. And then what I mean, because from the multi-scale perspective, modeling means different. I mean, if you talk about particle dynamics, actually I have one model above this is actually atomization. Some company approaching me now, how can the way we atomize it to get the quality powder need to be simulated as well, because they want to know what happened and how can we get rid of oxide, or for example, or scale, whatsoever. But if I'm talking about the powder-based fusion, which is spreading the powder, some research going on in the particle dynamics, spreading, swiping process. So they want to understand the packing density of the powder. So they use discrete element calculation. Again, this is classified as the modeling of additive, but it's not what I am interested in. The second is what I'm interested in, which is we call melt-pool dynamic simulation, or melt-pool physics simulation, which is a thermal-fluid dynamics. So it has to be something dealing with, again, it's different physics on computational fluid dynamics. So if you are in aerospace engineer, mechanical engineer, you may know about computational fluid dynamics calculation a lot in aeronautics. And this, we are very first one, I think in the world, I can say that we propose to use for welding and then additive manufacturing. And that's how our paper landed in 2015 in ACTA. And then next is about what happened now. What is a hierarchical microstructure that coming out, when you subject to different thermal cycle, and then that's depend on the precipitation kinetics. What happened to that? Some of you approaching me already about Inconel 718, which is the gamma double prime strengthening material. So what the matter? We need to know this because we want to understand now non-equilibrium microstructure has happened. You will not able to get the equilibrium microstructure at the nominal gamma prime percentage that you get from the spec, from this rapid sulfication process like additive. So how this emerge from as printed is something we probably need to understand a little bit, because if we do differently in terms of cross treatment, you may precipitate out some particle wrongly or not as you want. So again, this contributes also to grain size or texture. Texture control is also another matter, so we will talk more later. And another meaning of modeling, or another scale, I would say, we talk into the scale. This one probably in the 20 micron scale. This is about 100 micron length scale. This is about 1 millimeter length scale. And if you talk about centimeter length scale on the macro scale modeling, so this is now about abacus, COMSOL, or scale level of thermomechanical response, crystal plasticity, the finite element calculation. Anyway, whatsoever, just want to mention mole pool physics is a finite volume calculation. So you use different computational technique as well. Specifically, in my talk, we use the volume of fluid approach to go about it. People may use different approach, but for us, we use volume of fluid. And then someone also want to get an analytical function for this complicated process. But sometimes it's too complicated because it's dealing with different length scale. How can we actually get some way somehow to make a simple single equation that can predict everything? Again, this is equation and probably is a case-by-case basis. So another way to go for this model that I believe is not individual. This one is linked together. We want to link all this information and then going to reduce all the model. So that means you just calculate some rapid modeling tools that allow you to capture all the important feature in additive process. For example, thermal signature we call, and then sometimes I propose chemical signature as well. So you don't need to know just only thermal, but sometimes chemical signature. So from concept to material as well. So that's what I see. So before we going further, we just want to have 1 or 2 slides about the what we can do. So if you remember, I mentioned about functionally graded material. If you see this Eiffel Tower, it's actually copper at the base. And then this is the steel at the top. In between, this is a graded structure, which is almost is impossible in the traditional manufacturing process. Or you talk about multi-material, which is possible now in additive. People researching it. And this is the way, the model that I said to you previously, that's useful, thermofluid dynamics. So they want to design or find some way to functionally grade this structure rather than just joining them. That's why I'm saying this is joining just one line and there is just one interaction. But this one probably, yeah, again, if you want also collectively join together is also okay. So this have a graded zone, for example, in the 718 with steel 2324. I think this is also important in the high energy kind of application because this is more expensive than this one. And also graded zone will probably improve the property in the joining zone rather than just joining them, attach them together easily. So first is actually an example of the, I would say, example of the computational modeling in additive manufacturing. So we can use like material design algorithm to, I would say, ranking or screen out the composition. Let's say in this case it's nickel-based superalloy, published in Acta Materia in 2021. So we map all the, I think it's more than 100 nickel-based superalloy composition. But in the dot here, in the gray dot here, is about 10 million composition, which is actually calculated. And then you can map across the important 2 factor, which is the index, actually, strain edge cracking. Why strain edge cracking is so concerned? And the fishing length, again, this has to be told by metallurgy. So these two factors actually give an important for the defect formation and also the processability of the material. That's why we chose these two. Okay, I mean, there's an example of the kind of AI machine learning model that you use to screen out this material we call alloy design. So what I summarize here is that map the alloy space here with the high throughput computation, more than 10 million composition here. And we use physics base, which is, I would say, not really physics based, but empirical based on the previous understanding to estimate the printability and property. So this one is a printability, and this is a kind of defect or property. But more information can be found from this paper. We map over many criteria. We can show later. So index may include strength, creep, density, phase stability that you may find is actually useful from the previous alloy design framework that apply to some component already. So we try to apply this to additive manufacturing. And then for the material process, we try to, screen out from what we believe this is an important index. This may be informed from the lower length scale modeling that you did, for example, and then link to the index for the alloy design. Again, I just give you some example. We will dive into this kind of lecture individually in probably day 4, day 5, but this is just example. And then we have to, we can reduce some experimentation. We just select to some condition that we want, and then we engage with material supplier and user to provide us this. So after some screening of the 10 million composition, we identify the new 2 composition that we believe that optimize for additive manufacturing, as mentioned earlier. So we identify this, we call alloy by design, or ABD 900 AM, which is the performance of this is good at 900 degrees centigrade and 850. So it's basically a kind of another version of Inconel 718 approximately. So if you like, so this use a lot in Inconel 718. And then we compare with some property, ideal property, but non-printable material, which is CM247 and 939. We benchmark with this property. How can we get these 2 composition to get to that property? So again, this is something we use computational physics-based model to do that. So before we going to go to this level, and then what is the background calculation needed to allow this to happen? Because I believe everyone in this room, including me, want to do alloy by design, alloy design. So find new composition, find the genome of this. I said to one of your colleagues earlier that I forgot to use this word that are actually popular in UK now. We call material passport. What I'm going to tell you at the end, we will got to get material passport, which is contain the composition, processing, property, structure in one package. And then you go to industry, and this passport can be uploaded to another machine. Again, have to be machine sensitive as well, additive. So a specific machine model, and then you can work. And that is the ultimate goal for alloy design or metallurgy or mechanical engineer people. So that is the goal, the ultimate goal. So I mean, I don't want to recap much about this. Just want to go to the understand the real bulk of the result. Sorry, not result, the content. So just recap again. What does it mean by each composition? Again, I think this is a recap, but yeah, shall I start here? So what we want to know is actually the processing microstructure property relationship in AM. How can we simulate it? I think this is the key, because if you can model only melt pool, what's the point? What's the use of it? There's no use actually. So we need to know more than that, just a temperature field. Why this is so helpful? So from the material, feedstock, heat source, and interaction, we need to do something going about it. And then microstructure to understand the melt pool dimension, geometry. solidification characteristic, and then subsequent microstructure information like texture, grain size, and then mechanical property, both static and dynamics property. Static is strength, dynamics is creep or fatigue, for example. And then you see here, this is Inconel 718, which is actually non-printable material. So we map using atom probe. I think here is at University of Oxford, and then we map across the around crack area after printing. It's at printed condition. You will see that the stress field is actually not homogeneous inside the grain. Again, this is pose another challenge because this process introduces some kind of non-equilibrium microstructure again in this level. You see, this is red zone mean hard or quite hard, and then soft and hard in one grain without any, how to say, we need to do something about it using post-treatment. But if you don't know this, how can you do it? It's not just simple plasticity problem like in forging that you can homogenize using heat treatment anymore. It's more than that. So how can we go about it? And then we're using high resolution EBSD. I mean, basically, this is a sample. We map this one, and then how can we link this up and then give some guidance or some suggestion to the probably material development people to improve it or feedback somehow. So we will want to feed this information back to the, how to say, alloy design loop, if possible. So that is the goal. So again, this is just to similar, but not the same. But this is more detailed. Like this interaction actually gives rise to different solidification and hence the structure. If you know the pathway of solidification well, yeah, you may be able to change the microstructure from columnar to equiax, which is actually preferable in terms of the strength. And this is actually has first published in 2016 in Nature by the people from USA. Again, this is a concept of incontinent use. Again, apart from this processing challenge, we also have the residual stress or solid mechanics challenge or defects after that. So that's why we have a lecture here, processing and then defect of microstructure control. So again, I think we cannot see this for some reason. I think this is a technical problem, but I apologize for that. And then I think this is similar to what I showed earlier. So how can we actually simulate this to get the structure, tell something about component here to reduce distortion? That is the key. And then that's what I call process science or processing science. And then this is, again, this is similar to the previous slide this morning. But this is something different now. So, for example, if you want the process more powerful, you may need to understand the process. That's the thing. So, I mean, as I said before, the selection of the process is important for different materials. Let's say this is a kind of extract characteristic, briefly, from this review article, Progressive Material Science by Professor De Broglie in Penn State, saying that, I mean, summarized very well that if you want to have very high power, it's basically actually direct energy deposition process. And also, if you want very high production rate, if you like, is actually PBF, because you see this one is small, but this is high. But if you want a larger build, you need to use DED. But again, this is a compromise because you won't get the resolution you want. The resolution is relatively low or medium, not very high, based on the resolution based on the characteristic of the process and the feedstock resolution. And this one contributes to roughness as well, but some application require roughness. Again, that's what I said. Process, material, and fabrication has to come together as a package. So the surface roughness for biomedical may be good for the cell growth, but may not good for the rotating part in jet engine, for example. Again, this is something, so many criterion that if you are going to be ML machine learning or AI, you may need to understand this. I think it's almost impossible. We just assume from data, and then we need to have a knowledge-informed algorithm somewhere, somehow, to screen out algorithm for process. Because if this is simple engineering things that you can select it with confidence, right? And then processing, again, this requires further study whether or not it's needed or it's actually okay, or what is the process requirement for this. Again, if you understand from the interaction of the material, you may be able to tell something or guide something to the relevant engineer. So just a quick recap. I mean, this is quite a lot, as I said to you before. With different atomization from water, gas, rotary, plasma, rotating electrode, this gives rise to different printing. And this is so many factors. We say is so many control. I mean, something that we need to control with different geometry of this contribute to printing is proved here already. No doubt about it. Also, if you use wire and powder, it's also different. So wire is actually deposition rate is high. Melt pool is big, and also again surface volume is actually. There is another problem for the oxidation resistance. Let's say if you can print something like this, but it's similar to the FDM machine that you have in polymer or plastic. As you print, you will see some kind of layer here. But that means you may need to do some treatment somewhere, somehow. That's why hybrid manufacturing is coming. And yeah, but anyway, later, I think this is, I recap already. His source model, I'll show. Another important thing is scanning pattern. So, I mean, I just want to say the inference of this also published in our process parameter. You see here, this is a smooth track, but if you increase the speed a lot, this is a balling effect taking place, and this actually contribute to print quality. The scanning pattern also contribute to the final product. This is just a layer thickness, a simple process parameter that we study at the very beginning. It also contribute to the porosity level as well. It's kind of cheese here, a lot of porous. It's not, you're not gonna find the plane with this structure, I'm sure. Again, my model now will try to predict and talking about this. But in order to give you one example first, I think the process parameter control can be used to do like this. This is a melt pool. You may look like, and you see the bubble creating here. And this melt pool can be actually used to melt different material here. We call in situ alloying. So let's say, for example, you have titanium and nickel, or titanium and nitinol here. You want to mix it under the beam. It's so-called in situ alloying, that the model can give you some information about chemical signature and also defect formation. And if I look at from the top view, and you will see this is how things melt together. It's so amazing, isn't it? But this is actually using the multi-phase CFD solver to get one simulation. It's probably take 1 week to calculate this one, but it will be useful for sure. I can show you a lot of example that we use this result to compare with, for example, chemical profile measurement from EPMA or from very high resolution measurement. That's basically quite match on average. So another problem is defect. I mean, again, this is, I don't want, it's quite overview, but you will see there's a lot of defects here, or surface roughness, or lack of fusion. Yeah, in order to go about not only processing defects, that's going to capture next lecture, I think in day 3. This is what we need to solve. I'm sorry for a 20 equation here, but it's actually talking about the balance between the mass equation, fluid flow, which is the momentum. This is a Navier-Stokes that you solve for CFD. It's a mass balance. And then we use a volume of fluid approach here, and you have the surface tension as a function of temperature. I mean, this is also available in the Nature Com paper published early I mean, end of last year. So there is so many things like this term contribute to the vaporization. And then this actually damp the velocity in the solid. So it's around only in the liquid. This is a numerical approach to treat that the solid part is treated as a viscous, extremely viscous liquid. So this is approximation in this kind of calculation. This is actually multi-phase solver. And then in the thermal, we can add the thermal term like laser profile, whatever fancy term you want to add, or profile. For example, there's some research talking about the change of the beam profile, which actually only limited manufacturer can do that, right? For the beam profile changing, like ring donut or ellipsoid or Gaussian or blah, blah, blah. That contribute to microstructure development. I mean, this can be done in principle. I mean, anyway, what I said here, welcome for collaboration, any of them. Or vaporization is some mystery. When I say mystery, because it's actually based on the assumption of ideal gas at the moment. That's balance between at the surface of the metal and the liquid metal and the atmosphere, or the gaseous phase. And then we balance the phase there, and then we assume that this behave like ideal gas, which is not whole true in the extreme rapid suffocation condition. But anyway, that is a working model at the moment. And then radiation rate and heat has been taken into account to this term. So we use volume of fluid. In terms of solute diffusion, again, you will see that we use from momentum, balance of momentum, balance of energy, or thermal. We also need to incorporate some thermodynamics as well through this solute profile. This is actually complete, almost complete version of the model you can imagine. So, for example, if you are dealing with some simple elemental powder, you may not need to concern about the interaction between different elements. But if you are looking at a multi-component system like nickel-based superalloy or tertiary system, you may need to think about how can you model it in detail, if you like, in the microstructure development. So again, this one proof itself is a multi-scale problem. So for example, if I'm dealing with nickel-based superalloy, I would treat this as a pair calculation of nickel and X. X represent all the principal elements that used in nickel-based superalloy, depend on which grade you're talking about. But this is up to 15 elements. So this is quite heavy calculation anyway. So there's some solidification model that you need to use. And then you need to take care of, from this, you will need to define, we call mass transfer for soluto. That means segregation profile of some certain element. Again, we can neglect this one, focus purely on this. Again, these are all the things I want to talk to you in this hour. And this is an example. I think the way we simulate it, there will be a kind of specific session on day 3 that I and my postdoc will join online, will walk you through some software that we use and how we implement it to do this high fidelity, we call high fidelity simulation. But for example, if we want to use this to actually understand the alloy dependency on the different grade of nickel-based superalloy and extract something called thermal characteristic, you will see that just one calculation, each alloy composition at a given process condition. Some of you may argue that each alloy has different process conditions. It's true. But for the sake of comparison, we need to use the same across to see the effect. Why this one doesn't print well is you will see it doesn't melt well as well. That's been a lot of lack of fusion. And it's evident by this thermal cycle that CM247LC, which is non-printable material, is actually high cooling rate. And also that contributes to the subsequent big distortion happening during the printing. And that's why you will get this tear off or bend it a lot. And this is just simple calculation to use this high fidelity model to give insight into some material that you want to select to print, for example. That means things required for this material to take care of. So different alloys have different thermophysical property. Everyone know. And this thermophysical property can be calculated from the thermodynamic software like JMAT Pro, Thermoclock, something like that. To get, if you say you decide a new composition, for example, there's no data available in literature. You may need to calculate based upon some result, previous result, and that's fine. And composition dependency will give rise to the microstructure and property for sure. And that's the one application of this crazy kind of modeling things we do. And another one, we can use this to approximate roughly the porosity of the materials, actually. So we can, for example, if you actually decrease the scanning speed, the porosity will be actually decreasing. As you know, you have longer time to melt, and that means the fluid can do that job properly, not too large. If it's large, it may solidify and leave the pore behind, for example. And this is another thing, is actually just simple inclination of the melt pool can probably tell you about the microstructure already. So some of you may puzzle why this so matter, just single melt pool, why it tells so much. But I want to tell you so much that you can extract for ML or machine learning AI as well. But if you do properly, so you will see that different inclination here may suggest different grain or dendritic formation if it's dendrite or it's a planar growth or cellular growth, because the characteristic length, the length scale, the microstructure during additive almost is mostly non-equilibrium. It will be cellular structure, not quite dendrite. It will be very small, fine dendrite. We'll say to you more later. And this can be used as well to predict surface roughness, which is concerned for number of applications. That if you want to control it, I want to do some processing, but I want to understand now this process condition may give me different surface roughness, or even we can do it because from the industrial perspective, they want to minimize the manufacturing step as many as possible, right? If the process can give your perfect surface roughness profile, it's good. So we don't need to waste more money for post-processing. That is the idea. Or even we will understand and control it if it's actually detrimental. Yes, please. I can't hear you, sorry. Yes. Yes. We do for 5, 10 layers. Again, it depends on which process route you're talking about. Yeah. LPBF, yes, we can do up to about 3, 4 layers in this length scale, because I believe you appreciate that the time taken for 1 millimeter model may be 1 week, something like that, if not less. Yeah. So it's actually quite heavy calculation. But for some important condition, important material, we can run that for field condition to understand this roughness. But especially the roughness will be used a lot in the structure lattices. So the scale that we simulate is similar to the arm of that strut, which is in the micro or few hundred micron length scale. So it's quite relevant length scale. But I'm not talking about big component like 10 millimeter now, yeah, if it makes sense. Yeah. We can talk more later here. But again, when you say cracking, it's different meaning for different people as well, because what does it mean by crack? If I map over 10 by 10 millimeter here, you will see there is so crack in different level. We publish data here as well in Acta Materia. You will see at the surface, these are, I think due to scanning pattern sometime, and the internal is a macro micro cracking. Again, this we will talk in the next lecture. So we can understand some way somehow from the melt pool, and then looking at different alloy composition, and then scanning pattern, and then link to the final property to define something called manufacturability of this. So I think this is just the opening for you to see the whole picture. And this is the typical characteristic microstructure for AM, LPBF especially. So along the build direction and in the transfer direction, you get different microstructure clearly. And this structure actually, when you zoom in, is actually cellular structure. And along the build, if you zoom out a little bit, this is actually, you will see some zone like this. That's what I call solute tapping zone. And this is actually quite important. And then you will see this contribute to different microstructure locally. So you have equax and columnar mixed together. And this actually very important to understand, because if not, we may choose the wrong condition, especially if this part is just 200 millimeter thickness. And then this is important for implant, for example. But I mean, in this case, it's nickel-based superalloy, not implant. But give you some example. This will be better. So, for example, I give some. This is just overview for modeling different length scale. You will see we can use this model to predict the heterogeneity in the powder-based fusion. I mean, nickel-based superalloy. We published this already. Sorry, in Nature Communication. I think early this year. I think 24 or end of 23. Yeah, so you will be able to predict some kind of, you see, ripple here. And this is the niobium segregation profile. Because niobium will form the lava phase, which is brittle phase, is detrimental for the structure. If this phase is formed, and that mean it's so bad. So the life of the material will be decreased significantly. So we want to understand this as well. Again, just to summarize on this part before we going deep into that, is actually we saying that the number of metallurgical manufacturing available for fusion of different similar material. When I say this similar, means for in situ alloying, for welding, or for many things. Yeah, the feedstock, how to join it, whether powder bed or direct energy, using laser or electron beam, all matter what you need to use to know. And because you need to understand the interaction of the heat source and the feedstock, and then quality of final product depend on this combination of this factor, which cannot be compromised, I would say. And typical microstructure is very fine and textured. Certification will determine the growth rate and thermal gradient under cooling, blah, blah, blah. And this can be tuned by scanning pattern. And then, this can be tailored as well. Static property like stress, surface condition, size orientation can be controlled, I would say. And dynamic property, again, is something more to research. But we believe with the information of defects and then surface information and the microstructure information, we can estimate that approximately. So this is the first part of the this. And then now we're going to the more understanding of the fusion welding. So this is the second part. So we going to use or understand now more on the powder-based fusion. What is the process science for that? And then research method used is actually computational fluid dynamics. And then we incorporate this into material design. And then we have to capture all physical phenomena present in the metal AM, integrate them together, not only powder particle, which some assumption, but thermochemical fluid model as well to correctly predict the grain growth and the static or solid state transformation. And this hopefully will apply to digital material design later. And this is what it's meant by different interaction and then different physics acting on it. So we can talk a little bit more now. I think again I used too many how to say repeated slides. Sorry about that. But what I want to say here is that we have particle dynamics acting on here. Again, different set of equations. We have thermal fluid, which is all those 20 equations I show you. And we may have some solid state transformation. We may have another thermodynamics equation, a long set of that, for the solid-solid transformation. What I showed you previously, this is the solid liquid vapor transition, and this is a solid solid transition. This is another physics. And then you have the solid mechanics, which is dealing with crystal plasticity about the material life, like crack, fatigue prediction, for example. And again, this acting on just 100 micron length scale. Just right after this is a characteristic length scale in AM. So this is what I give some commentary article in NatureCom few years back. Yeah, and we are going to look at this from the perspective of this one. We neglect everything, just looking purely on the formation of the melt pool, what happened. Again, I will skip the part that's not relevant now or repeat it. So we use the computational method or integrated one, and you will see, I can show you the case that we did in welding. And then we use the high-speed camera to capture the dynamics of the welding. You see how the melt pool oscillated and what happened. We try to capture using simulation, solving all those equations before, and then try to predict the resultant microstructure. And this has been validated with the high-speed camera here at a different times chart here. And back in the experiment 2015, one of my projects, and you will see that this prediction is quite well and the condition investigated. And again, this is actually used lesser set of equation, which this is a reduced version actually from those equations. But anyway, you need to couple all this to basically solve that. So that means this is a minimum that you need to solve. There's a software company provided this kind of function as well. That's called Fold 3D, which is so expensive, probably 50 grand or 50,000 pounds a year of license, something like that. That's what I heard. Even this is academic, not industry. But we use an open source code actually. We code it up from open source software. But you just need to code all those equations if you like, yeah. So from the processing design, we're not going to say it's actually like a technology pull approach, because we not pull from technology, but later for additive, we say we need to use science push approach. That means you need to push the technology from science that happened in this and is still going on here. We're not filling the gap of the science that happened in this length scale yet. So a lot of synchrotron experiment, a lot of high-speed imaging things still going on, and still have some model to do. Like in additive, you may think about it, it's just that's it. No, it has a lot of application, like you use like friction stir combined with powder bed, believe me or not, or friction stir combined with DED, or you have ultrasonic with powder bed, or that's called field-assisted additive manufacturing. Again, that's not been discussed now, but just give you example. That means push for the process in science, how to understand this and design a new component with the property that you want. And this is the approach. So we actually need to link all this composition to process. What is the process parameter, process condition, and then link with the structure, what you want to get. Again, this can be used as indexes or output from your model, if you like, and then to link to the property of static, or we call time-independent property and time-dependent property, like creep or fatigue, for example. So we use different tools, and that means they need to have an integration component into the modeling. It's not just standalone model can answer everything. It's impossible. So we need to work across the globe to collaborate with someone who expert in thermodynamic calculation, someone expert in crystal plasticity, because no one can do it everything on your own. You need to collaborate to get the more impact. And that is some, oh, sorry. I'm not sure, for some reason it's not working, but this is a moving of the, I think it's probably working. Yes, this is, you see, this is a DED, but I'm not sure the light is quite sharp here. You see the melt pool is actually moving. And then you see the spot here is a laser, and sometimes you will see some sputter, some melt jet coming out. And if you focus clearly, there will be some plume of the vaporization, or of the vapor coming out as well. A lot of things going on in just such a small length scale. Quite interesting to me, because gas liquid solid transition give rise to, for example, this is a science paper theory on sputter. Vaporization hopefully coming out from us. Only one just published in NPJ computational materials already on this. Certification, whether or not it's dendrite, I think this is still clear already. It's not dendrite, it's a cellular structure. That means the way you model the certification may be different. And what is the grain and what is the thermal response and mechanical response. So if I dig down further, I mean, this one just an overview, you see from the top view. But if you see from the side view, for the sake of understanding what happened in the metal powder here, some of them are actually merged together, or coalescent together and flying away. And this is the experiment carried out in 2018 in States, in Oak Ridge National Lab, if not Argonne. I think Argonne National Lab, sorry. And this paper also published in Science as well. Summarize the interaction of this, getting the beam and then contribute to the defect formation, for example. What is happening if the argon gas flow domain here or vapor jet domain here, what the matter? So, and then we can compare this or contribute or capture this with the high-speed imaging that you may have to basically close the loop here, understand this. And to summarize the science which is actually needed to simulate this kind of thing, I think I would say all this is more about physics that needed to be simulated in the model. So I summarize into the powder dynamics. So you need to probably looking about particle arrangement, translation, vibration, rotation. So it's actually a large degree of freedom that you need to calculate. Because imagine if your domain has about 10 million powder particle, you may have 30 million variable to vary. So it's almost impossible, I would say, to calculate in such a large degree of freedom like that. I mean 6 as well, not 3. Sorry, 6. And then you have this phase transition, which is, again, it depends on melt pool here, or you're talking about grain or talking about solid state transition. It actually, this bullet point, each bullet point represents different modeling scheme that you're going to use to answer those questions. So again, for my lecture, I think I want you to get, it's not about how we model it, how we implement the code, but rather want you to get the idea how complex, how multi-scale physics actually acting in the process, which is actually quite amazing. Just one single bead that you can extract a lot of information. And in casting are different characteristics because it's just controlling the temperature is a fluid flow problem, but this one is more than that, for example. And then this length scale, this is something I'm talking about. This need to link to the, we call mesoscale full field simulation, which is you may use the different approach like representative volume element approach to link all information here to get macroscopic response for the component level calculation, for example. And this can be used to establish with the failure criteria in additive. Again, this individual bit here means probably different group around the world. So the question for the community in modeling of additive, which I'm going to chair one session next year in Italy, they call the 5th International Conference in Simulation of Additive Manufacturing. We have quite big community now, so taking care of different length scale that I'm saying here, and then how can we, the big question that how can we integrate all this information? It's not just about individual contribution, but how to link them all. In US, they have a program already existing based in, I think launched in 2018. It's called you may know about this programming called exascale simulation. That is actually to do that job actually. So anyway, whatsoever, I mean this one also keep me talking about science or interaction, what happened, that you may need to know and understand this, the signature here actually go up and down here, contribute to so many phenomena that happen. And then once you do heat treatment, aging, or hipping, this may have different defects associated with that. But how can we actually use the model that I said to you previously to screen out some way somehow or know some condition that may be combined and give a passport to one material that you can print out successfully. Again, this is a challenge problem. Research needed. It's not just simple thermal calculation from abacus can solve all the answer that you may want to know. Like defect formation is almost impossible. So example from experiment that inspire us to do simulation is actually the process itself gives stochastic nature for us to actually curious more. So for example, if you vary powder distribution, layer thickness, or scan speed, let's say in this case, layer thickness varied, scan speed varied, here, you will get different subsurface porosity or surface roughness. Again, this has been published and received a lot of, I mean, it's almost 1,100 citations already in this field. So we use CFD as well to rationalize why it happened like this. And then we kind of know that increase the layer thickness, you increase more porosity here. And if you increase scanning speed, again, the trend is not very clear, but it seems that there is a breakout point around this. So you cannot go beyond, I mean, 4 meters a second scan speed. I mean, it's probably common in our PBF system that you can, the spec of the machine we use, they said 7 meters a second. Believe me or not, but it's not true because we use high-speed imaging to correct it, and then the maximum capacity is just about 4,400 millimeters a second, which is the machine actually wrong to say the spec. But anyway, this is the big things we discover as well from the manufacturer point of view. So they said LPBF can increase a lot, but there is a limit, which probably need to study based on different material you are using. In this case, it's optimized using titanium 6-4. But different material has different characteristics. This is from experiment, but how can we model it? This is the key. So I will walk you through quickly on the modeling. I'm so sorry to give too long background, but I think it's important to understand what happened. And this is what we do. So what is the manufacturability we want to know, and what is the key process variable that matter? This is the two equations that drive our curiosity to do the modeling. So the way we do is actually, this is all the modeling framework we done and corroborate. I mean, mostly we done in ourselves, especially in the red dash envelope here. This is what I can do straight away on the swiping. I mean, this is simple model, particle dynamics. And then you do the melting. And subsequently, you will get to predict the grain structure here. And this information is heavy enough already. Before you take into, if you use incandescent 1.8 here, you may need to predict the gamma prime, double prime, gamma double prime, and delta, how to say, distribution along the build direction, which is quite surprised that you will see wavelength is not uniform anymore. And this information should be actually inserted into the mechanical model to predict the correct property that taking place induced by the signature of the process. And this, before we doing this, you can use this modeling to inform or model inform machine learning based model. So I think it's not the way, another way around. It has to be driven from science, as I mentioned earlier. So that means from this lower length scale to high length scale. And if you've done it correctly, you may be able to capture correct information needed to actually successfully print a big component application. So first modeling is actually particle spreading. Again, we capture everything from experiment that we have. So we use experimental or laser kind of measurement of the size measurement, and then we use MATLAB to fit the cumulative distribution function here, arrange the particle in this one, assuming that there's no rotation, everything's static. Otherwise, you will be in trouble. It's too much calculation. And then you spread the powder onto the bed, and then you do again to check if the simulated arrangement here similar to the experimental, which is yes. And then after that, you may actually want to print them. So thermodynamic is kick in. You will get to predict the single track here. It's complicated enough. As I said, using this kind of set of equation. Again, it may look a bit different, but actually the same physics we use. But the only difference here is actually we capture different phase transition model. Rather than using simple, but we try to explicitly calculate what happened in the interface. And after that, yes, this is the use of the model. And the model can use more than just for, not just for the sake of the complex equation here, but there's some usage. And this one just to summarize why using the model to rationalize metal additive manufacturing. Again, first one is actually understand the effect of the different laser mode. You may know some manufacturer provide with different modulated or continuous laser. And this one contribute largely to the melt pool characteristic in your print. So this simulation, level of simulation, give some insight into that, first of all. So you will see here, continuous, you see the blue large zone here. This is a fishing range zone, is a machi zone. This is quite sensitive. If we can reduce this zone to be quite thin, and then the crack will be minimized, for example. Second is to understand the alloy dependency in AM. Let's say you have first material, as I said, very thin blue zone, which is a machi zone, compared with alloy number 2. You have quite large zone. This actually contributes to cracking, for example. So this is not preferable. You want something like this, for example. So this is the use of the model, if you like. But without model in this length scale, it's almost impossible to get this information. Again, this also has been shown already as an example previously. Understand different alloy composition. And then we use this as well to predict the porosity-induced surface information. So we ran the model because, let's say, if you vary just one parameter, it's complex enough already. You spread the power first time, and you spread the power second time. I strongly believe that the arrangement of powder are different. Is that correct? But that means important in additive is actually, for experimentally, computationally, it's not actually deterministic, it's stochastic. And then what we need to predict or capture is the stochastic nature of it. So what we did, we ran 5 times, we spread 5 times, and then we print single track 5 times as well at the same condition. And then we extract, for each condition, we extract the kind of distribution of the subsurface porosity. And we put it in error bar, I mean in different thickness, 20, 40, 80, and 100. And this one, if you see the circle and regular, square dot here, quite aligned with each other. So the predicted porosity level using representative distributed powder arrangement is actually give quite good predictive capability for the system investigated. Rather than using simple regular, you will overestimate or underestimate the level of porosity in the build. Yes, and then you can, this is a model, this doesn't look like experiment, but this is model. Sorry, this is experiment and this is model. So we zoom in some area in single track, you will see this also published in this paper, also quite about 400 citation as well. you will see it's captured the general characteristic of the process quite well under condition investigated. And then this is actually where, I mean, the roughness we actually test in the nickel-based superalloy, previously in the titanium 6-4, using the micro CT. Again, this is single track, this is a balling quite rough. Again, and then subsequently you will see it's probably smoother surface, but not ideal. And another thing is actually using model that I mentioned. I mean, you may familiar with the weldability diagram. I think I didn't show you, but I show you previous lecture. So rather than just based on the empirical manner, we actually calculate using CFD to predict a range of nickel-based superalloy property. So we vary two things, which is viscosity and then conductivity. And then this actually, when I map, again, I have to say I map 100 nickel-based superalloy available in literature into this map. The blue dot represent wrought superalloy. The red dot represent cast superalloy here. You will see that there is some window that actually turn green or blue. That means more printable in terms of porosity, in terms of cooling rate, which contribute to the distortion later. Cooling rate means different as well. Cooling rate from liquid to solid or from solid to solid. That has to be clearly declared. So in this case, we have in liquid and solid, which contribute to distortion, for example. And then this is a sweet spot that we can select some property that in this window. And you know, I actually map with the printable nickel-based superalloy as well. It matches quite well with this kind of CFD-based process design approach here. So we use from fundamental CFD, we use the Reynolds number, which represent a measure of the fluid flow ability and also platelet number for the heat diffusion to actually screen out some condition. Let's say in the red spot here is not useful. We need to go to the bruise window here for better design from the process perspective that contribute to the indexes for the alloy design, for example. Like you try to control that, okay, you prefer probably thermal conduction or thermal, diffusivity of this range, for example. And then this one will then feed into this kind of processing simulation, and then we can do something like elemental additive manufacturing, which actually at this one I'm trying to extract the characteristic of the AM process. I think we published in ACTA Materialia as well to look at two parameters, which is diffusivity and viscosity, and you map across the transition metal in the periodic table, and you will see that interestingly there's a different material property across this one, which quite clearly different. So if we interested in a main metallic system like iron, titanium, nickel, tungsten, aluminum, and gold here, at the same process condition, you can extract characteristic of the melting very well. For you can see that for gold is actually keyhole mode, while some condition here is actually just conduction mode, but keyhole but shallower, but some is with porosity as well. That's what we did. So we can see that from the mass loss perspective, the heavier element show large mass loss, and then the metal in the 3D, 4D, 5D group, mass loss, if we normalize by the atomic weight, or we call molar loss here, is similar range, but it's more sensitive to Reynolds number, which is the fluid flow of the material here. And then you can show that there is a trend in the Reynolds number map with the mass loss here, rather than it's a bit confusing in the thermal indexes, which is platelet number here. So this information will feed into the work of the in situ alloying, because ideal world, you don't want to atomize actually the powder every time you want to create a new composition. You want to create it on fly using laser. So this is the idea that, for example, nickel titanium, you want to mix it using laser, something like that. How well they mix together is important to know, and how actually we can compensate the composition loss, that is another matter. For example, if you know that alloyed powder will lead to 0.3%, 3 atomic percent loss of nickel, you can compensate about, okay, rather than 50-50, you may choose 47-53. And then just simple kind of idea that we use, and which is true. We need to compensate a lot to get finally 50-50 in the final build to get the correct property we want, for example. So we also doing the, multi-material deposition as well in the refractory metal. And this one focusing on the application of repair. When you want to repair some kind of high temperature rocket case or nuclear application, you may use some refractory materials, like in the where is niobium, moly, tungsten, tantalum. The problem is that tungsten doesn't actually join well with the base material. So that is the inspiration why we conduct this work. And then you will see that when you fabricate, first layer is actually, the substrate is nickel. We fabricate titanium like this. Yeah, like the substrate is titanium. We have molybdenum, titanium, molybdenum is alternate layer. And what we found is that different, print strategy give rise to different mixing behavior. So for example, if you look at from the longitudinal section, and this is the ranging the liquid density, you will see tantalum is a kind of laminated structure. So it doesn't mix very well with titanium. And then for hafnium, I think it's probably mixing better. This is tungsten, which is the problem that why you get a lot of crack or lamination because from the thermofluid dynamics understanding, they say that doesn't make very well. So we need to fine-tune the condition to make this mixing happen, or using some different way to mix it. So from the longitudinal or the cross-sectional area, also say that this is quite laminated for tungsten, but it's probably better in tantalum or zirconium niobium, for example. And then once we use this one, we're talking about different length scale of modeling, which is the grain structure. So we want to feed information from the CFD to predict the grain formation. Again, this is a zigzag pattern. When you have a different scanning pattern, you will create different microstructure. Again, I will have individual bit of this. I will have a lecture to go in deep into the detail how we calculate, estimate that. And this one you will see, we can capture, if we can simulate the thermal fluid here from CFD, and then we export it into CA, which is cell automata, we can at least capture the trend. But it's not ideal. I would say better way, but more expensive calculation. So this is just a proof of concept, and this may be enough already for industry to develop some microstructure-based process design, for example. Again, there is another 2D simulation for titanium 6-4 in the microstructure length scale. So what they do, if you remember the cheese line structure, using phase view, again, this is different technique. They can predict a kind of processing map from this simulation. So this is the ideal scenario that people want to do in the modeling community, that they want to predict all these map with the microstructure and the porosity defect. So this one is actually strongly coupled. It's not being detached to each other. And next length scale is actually more on what is the use of the nanoparticle like tungsten carbide to the copper, because copper is high reflectivity material. That means it will reflect a lot of energy from the laser heat source. We need to find some material that absorb energy to basically, confine energy into the domain to melt something. Otherwise, it will get lost by copper, because the absorptivity of copper is actually about 5 or less than 5%. That means 95% loss if you do it. Let's imagine this is a challenging for modeling as well, and then simulate and then experiment how can we improve the processability of copper. So some people using a more high absorptivity material to use. For example, this is tungsten, and then they try to use tungsten to melt copper, for example. And this is another work that they can use the reinforced particle and then try to predict the microstructure if you use reinforced particle. And again, this fall into the microstructure simulation, which I will talk more separately in one single long lecture as well. And again, this is a precipitation model that I said to you. If we try to do the blade geometry like this, you see in inclination 1/8, when we fabricate it, according to the thermal signature, you will get some kind of wavelength or the scatter of microstructure. At the base, there's longer time for material to respond, so you get some distribution of the precipitation at the base of material. And then that means you may get high distortion from the base as well. And that justifies why it's actually bended, during printing, blah, blah, blah. And this understanding can be used after to actually fine-tune the process condition, because once you know the initial precipitation, you may be able to use some simple mean field equation to predict what happened after the thermal cycle that you use during aging and heaping, for example. And this will contribute a lot to determine the material life. For example, as you know, we use the distribution of the gamma prime, for example, for the life of nickel-based superalloy. So if we know the profile, the size of the secondary phase, we may be able to predict the life of the component. That's why it's matter. So, but another level is actually residual stress distribution. Life is so complicated in AM, and the distribution of the stress evident by neutron diffraction in Oak Ridge National Lab is not actually symmetry anymore because of the process that I mentioned earlier. For example, some condition, bad condition that contain some porosity, your residual stress profile will be changing as a dashed line here. So asymmetry here can be captured as well using Abacus simulation. I will talk to you more in another days. And then we can use this one to decide the chemical process design for AM. Again, this is just to wrap up what we do. Actually, once we can do elemental AM, this is the kind of design space that we are talking about for a number of advanced material that we can looking at for different application here as well. That is the argument for the process science that we use for this multi-metal deposition here. So I think there is some repetition. I'm sorry about that. But I think last but not least, I think this is something I want to say, because I think I see the time is quite coming now. So the key, what I want to say for additive manufacturing is that we want to have something called process-induced microstructure, because microstructure induced by the process, and the structure inform property, because structure also influencing the property to get the kind of design space here. And then when we know property, we can actually feed back into the process what is the condition that give rise to this property. So this one is actually pushed from the science, as I said, and we call this one ICME, or Integrated Computational Material Engineering Approach. And this one will get I mean, different microstructure, definitely different property you may expect it. And I hope that this statistic from stochastic nature of the process can give you the relationship mining for the composition process and structure, and hope this framework can allow you for material discovery. Thank you very much. I'm sorry if it's too fast, but any question, please. Yeah. So I hope this is the overview of the modeling of additive, and it's not just simple thermal model that you may think, okay, use one pass of thermal model can solve everything. It's not like that. It's more than that, a lot more than that, trust me. And then a lot of science papers still coming out, a lot of nature papers still coming out for additive topic, especially to understand the very fundamental aspect of it. Because sometimes the equation I show you may not, I'm not saying it's wrong, but it's just representation of what we think it should be in the process. But if we discover new science that we should incorporate into the model, that is a plus. And again, when we study more and more, we start to see more scientific point that we need to add, or actually term, for example, in the model to improve the understanding. And I hope this gives you the overall picture of mechanistic modeling of additive manufacturing. And then we will talk more in detail for individual aspect of it in the day or two. Yeah, thank you. Any question, actually? Yes, please. Yeah. Morphology of. Indeed, indeed. Mm. Yeah, but when yeah, because what? You're not going to use the full maximum energy to melt your powder, because it will be sputter everywhere. You need to find the optimum lowest power possible that you can melt without any defect, right? And that means the morphology contribute to the defect, like lack of fusion, for example. The morphology contribute to the gas porosity, gas trap porosity formation because of that nature, and because of they have more, less surface area, if you like, if you think about engineering aspect, normal. So less surface area than spherical, because it's elongated, right? Not circularity. It's actually away from circularity. And that contribute to, you will see a lot of paper in additive manufacturing talking about effect of that. Another factor of the low quality powder is that you may introduce some gas trap porosity inside the powder. And this actually contribute to the final product defect. We already published this work as well in NatureCom on the detailed pattern of the fluid flow that make pore coarsening up to probably 0.5 millimeter, quite large pore, which is detrimental for aerospace repair, for example. So I think yes, the key things is that we're not gonna bang our powder bed with high energy to make sure that everything fully melt, because you will introduce keyhole defect. You just want to go to the boundary of the conduction and keyhole mode. That is optimum condition where you can melt it without or minimum defect as possible. So that means all factors contribute to the defect. Yeah. But another way to go about it is actually you may design some machine learning algorithm after you understand this from experiment and model, and then find a better condition for this. Again, this is another story. Thank you. Any other question? Yes. Yeah, we have a paper on ternary system. It's a heavy calculation because if you have two phases, if you have two material binary system, you need to solve 7 phases, because liquid, solid, vapor, liquid, solid, vapor, and then you have the gases environment as well. So that means it's a 7 phases calculation rather than 2. If it's pre-alloyed powder, you have only 2 phases. But if you have 3 or tertiary system, you have the phases up to 10. we did it as well with titanium, zirconium, copper. But this is a new alloy for medical application. It's so heavy calculation. But again, there's some commercial software that offer you as such as 4-3D. Extremely expensive one. Yeah. And then you don't have any flexibility in tweaking anything. Yeah. We can talk more about that. I'm working, and then we submit paper on that already with the detailed microstructure. Quite interesting, that one. Yeah. Thank you. I'm so listening.
So then we'll take a break. First we will go to the group photo at the opposite to the library. Anyway, I will accompany you. We'll take that group photo and we'll come here and take a snacks, and by 4:10 around we can start the next session.
Is it too heavy? No, it's too fast.
The subject matter is that way.
Okay, it's that way. Huh?
Yeah.
Because if you want me to go to the detailed equation, it's not.
No.
I think this is the way.
Yes.
I also give one.